Bismillah ar-Rahman ar-Rahim. Heat capacity and latent heat. We will mention two items. First of all, specific heat capacity is defined as the amount of heat required to raise the temperature of 1 kilogram of a substance by 1 Kelvin. In SI system, items of it is joule per kilogram per Kelvin, 3 items. Now we come to heat capacity, which is defined as the amount of heat required to raise the temperature of a given subject by 1 Kelvin. So we were going to remove the kilogram in the previous item. So it will be joule per Kelvin. I'm sorry, joule per Kelvin. You see, Kelvin is commensurate with Celsius. That means that they're equal to each other. So we will use later on Celsius. In vaporizer, of course, the components of each of the vaporizer are has its own heat capacity, so we can calculate the amount of the total of it. And we said it before in vaporizers. This is specific heat of the human being, which is you must memorize, is 3.5 kilojoule. Now we come to kilo. For each kilo, for each Celsius. You see, the total is being rated on the other side whenever we mention a patient with 70 kilograms weight. Suppose the patient loses temperature and becomes 36, so we can calculate from the item mentioned before the amount of heat required to elevate 1 degree, knowing that this process is made by shivering, which will increase the total heat from 80 to 320. So we have an extra 340. Whenever I might multiply per 60, we'll get an amount. This amount needs around 17 minutes for the patient to shiver to regain his own temperature again. Of course, this is a body heat content, which is the multiplication of the mean temperature time the heat capacity of the human being. 4.18 kilojoule are required to raise the temperature of 1 kilogram of water by 1 degree Celsius. You ought to memorize. In other words, the specific heat of water is 4.18 kilojoule for each kilogram for each Celsius. Now we are using Celsius instead of Kelvin, as we said before. The specific heat of most of the substance as blood is less than water. This is why we use it in vaporizer to make the temperature steady. The specific heat of blood, as we said before, is less than water. So if you have 2 kilograms of blood, in other words, 2 liters, and we want to raise the temperature from 5 to 30 to 35, so that the patient will not be affected and lose temperature. So this is the figure required whenever I want to measure the heat capacity, this amount of blood, knowing the specific heat of blood. This amount, if it's not supported by enough heat by heat warmers, the patient will be affected much, losing temperature, and he can lose, and the temperature may reach 36 if we don't heat this amount of blood. Now we come to the gases, which is very important. Memorize also has a heat capacity. The heat capacity is almost one kilojoule per kilogram per Celsius. 3 items, you see. So we always mention, we don't like to mention gases in the form of kilograms, so we measure it in a form of volume. So instead of it, we can say that the amount of heat is 1.2 joule for each liter for each Celsius. So this difference is around 1/1000th of the figure before. This means what? This means that it's very little amount is needed to elevate the amount of air or whatever gas, and at the same time it loses its heat very speedy. In other words, whenever the patient inhales cool gases, it reaches the upper airway after a while, losing its temperature. This is of course a good sign of or the importance of the specific heat of air to be low, and this is how to figure out, of course, the amount required to increase the temperature of an amount of a gas. This heat required by the human being to elevate this cool gas is definitely less than that required to humidify this amount of gas, as we will show later on. Now we come to the second item, which is called the latent heat. Of course, we have latent heat of vaporization when the change of a liquid to a vapor. We have a latent heat of fusion when a solid changes to liquid, and lastly, we have the latent heat of crystallization when a liquid changes to solid. Now we come to the third definition, which is called specific latent heat. Is defined that the heat required to convert 1 kilogram of substance from one phase to another phase at the temperature concerned. You must mention this. And the SI system is made of two items: joule per kilogram. Joule per kilogram. The specific latent heat was joule per Kelvin, but this is joule per kilogram. So, for instance, I want to convert water to steam at 100. We need around 2.26 megajoule. Now we come to the megajoule per kilogram water. This is the amount required to transfer this liquid into vapor at that temperature. This amount is being decreased, of course, if the liquid is being, it's increased if we want to shift it to a steam at the human temperature, 37, which is less, 2.42. On the other hand, if at the room temperature, it reaches to 2.43 megajoule. So this figure you ought to measure in whenever you are required to put an example. The latent heat of vaporization, of course, whenever the heat of the liquid is much larger, the heat required to decrease, to shift to steam definitely will be decreased, as you can see from the curve. In other words, the latent heat of vaporization of nitrous oxide is almost zero at corresponding to the critical temperature of nitrous oxide, which is 36.5. What's the meaning of that? It is being shifted from liquid to vapor without addition of heat. This is the explanation of this item. Latent heat in anesthesia. You have ethyl chloride, which is being stored in a compressed bottle, of course, for it to be in a liquid solution. So whenever I create by pressing fine drops, this drops will definitely cause cooling of the area of the skin, and this is capable to for us to abolish, of course, the sensation and remove absence of whitlow. Of course, the liquid vaporizer, whenever they are vaporized, they lose their heat from the surroundings and from the liquid, needing more heat. So, of course, most of the vaporizers has thermostatic devices to compensate. Of course, this is a nice thing. Whenever I open the nitrous oxide cylinder very speedy, of course, the transfer of liquid to gas needs too much heat. This heat is being taken from the surrounding and from the liquid, and then this will decrease definitely the pressure inside the cylinder by time. And the way to return back to the pressure is closing or shutting off the cylinder, so that the pressure, as you can see from the figure, is returning back to its level whenever I close the valves. Carbon dioxide and cyclopropane are, on the other hand, stored in the liquid form. This liquid form is not much affected by cooling, because the rate of taking off of this from the cylinder is very slow in comparison to a nitrous oxide. Now we come to the four item regarding this system is the oxygen tank. As you can see, the oxygen tank is based on the critical oxygen. Of course, temperature is not minus 119. You ought to memorize this. And the liquid tank is much more economic than cylinders. It's made of a gigantic vacuum tank, as you can see, where the nitrous, where the oxygen is being liquefied and is being transferred to vapor. This vapor coming out is very cold, so that we have a super heating coil. The pressure of the tank is 7 bar, and whenever it's released from to a system of pressure, it will reach as the pipe system pressure, which is 4.1 bar. We have two situations. Suppose the takeoff of oxygen is much more increased in some situation. This will take much of the latent heat, and the pressure inside will decrease and the temperature will increase. So to keep this system by the too much taking off of oxygen, we have what we call a pressure raising vaporizer. This pressure raising vaporizer senses the temperature and the pressure inside the system. This is capable for it to take more oxygen, liquid oxygen, and heat it and giving it back to the system, in addition to what's coming from the upper part of the cylinder, to compensate for the much increase in the take of oxygen. You see, so this is a compensation. The other thing is, whenever this tank is being closed off and kept for 1 week, definitely the pressure and temperature in it will increase. So for safety, we have what we call a safety valve. This safety valve is capable to be open to release much of the oxygen present to keep the temperature and the pressure constant. This is a hint about the oxygen tank. Now we come to the effect of humidification of the dry gases whenever it reaches the human being. Or normally we need 34 milligram water of vapor, for each liter whenever this gases reaches upper airway. This, of course, normally it happens, but it's being taken this amount from the mucous membrane. So if it's taken much of this mucous membranes, it will cause hypothermia, which will affect, of course, the small baby. So this is why we ought to humidify the gases. The figure written normally is around the loss of around 11.6 watt normally, as we mentioned before, from the 80 normal basic heat content of the human being, which is more in case of inhalation anesthetics, because inhalation anesthetics are very dry, needing more support of water. This makes a difference instead of 10% loss to 15% loss. This is a hint about heat capacity. You ought to know the figures is very important. It's not a difficult subject. Wassalamu alaikum wa rahmatullah wa barakatuh.